Okay, so so our main theorem was this one. You see my the PDF file, no? Just a moment, Martin. You see?
Yeah, I see it.
Okay.
Yeah.
Anyway, this is the main theorem. At some point we will prove it, and actually its proof is much more important than its consequences. But because during its proof we will see the notion of we will see Picard-Lefschetz theory, we will see Lefschetz vanishing cycle, Lefschetz temple, and a lot of nice stuff in order to understand the topology of algebraic varieties. And okay, so maybe and so today we will just talk about the consequence, Lefschetz hyperplane section theorem. So remember that we had this X, and then we take two hyperplane section Y and Z. They were intersecting each other transversally. Everything basically was intersecting any other things here transversely. And so Y, Z, X prime, which is the intersection of Y and Z, they are always smooth. And okay, so let's go to the one consequence. So you see that there are a lot of other consequences that I have put in the book, but we don't have time. So today is this Lefschetz theorem on hyperplane sections. And okay, so maybe let's just start announce the theorem. X is smooth projective variety dimension, and Y is smooth hyperplane section. When usually the people write smooth hyperplane section, the transversality is also there. I mean, sometimes hyperplane can intersect X in a smooth object, but it's not a smooth, let's say, in the scheme theoretical context, or it's not smooth in the sense that you assume transversality. So the transversality is implicit here. Anyway, so if you have this one, we want to prove that all these homologies are zero. And since we started with check cohomology, maybe you just put take this Q down and put it up. It's also valid. So you see that all the relative cohomologies, Q from 0 to n-1, n is the dimension of the bigger variety, must be 0. So maybe from now on, let's I start writing. Okay. Let's start writing. Okay. Direction. Okay, so notation already fixed. So we have this smooth hyperplane section, dimension of X equal to n, and if we want to prove that HQ, as I said, I will start using cohomology notation, and I will not write the coefficients in Z. So always coefficients will be in Z. In order to make the notation shorter, I will not write it, and this is valid until n-1. So we want to show this one. So in our way, well, I have just introduced check cohomology without proving any theorem, basically, about check cohomology. So the idea is that during the proof of this one, I will list all the theorems that we need for the proof. And if somebody has never seen algebraic topology, then he will see a lot of theorem coming from algebraic topology and without proof. And I hope at least he will get familiar with all these propositions. So let's go to the first theorem in. Well, okay. We want to make the proof of this one. So I will enumerate one. So let's before starting the proof, let's state another important consequence of this theorem, that if you have pairs of topological spaces attached to any pair of topological spaces, you have the long exact sequence attached to this one. And so let's write down this long exact sequence, HQX. So when I will start enumerating, this enumeration corresponds to all properties in algebraic topology that we are going to use without proof. Okay, so the long exact sequence attached to a pair. So let's say HQX. I will try to write down everything in cohomology, whereas in my book it is written for homology. So, okay. HQXY. And let's see HQ plus 1 X Y and so going on. So the first fact from the algebraic topology, that if you have a pair of topological space, then there is this long exact sequence. Let me explain a little bit what it means. First of all, it says that there are maps. There are maps from all these maps from here to here, from here to here. Some of these maps are a kind of canonical maps. For example, this map. This is just a restriction map. But for the moment, just assume that okay, there are maps. And this is a long exact sequence. What it means, long exact sequence, if you, for example, fix one of these spaces, then the kernel of this map must be the image of this map. So there are some information hidden in this statement, is exactly this one. The kernel of the map, let's say F, is the same as the image of the G. And this will produce a lot of restrictions on all these cohomologies that we are dealing with. So this is the first theorem from algebraic topology we use. So as you see, if we apply now this our theorem to here, what will happen? So if I assume that this is 0, this is 0. So in order to get to have 0, what I must have, I must assume that Q is bigger, less than n minus 1 in order to have this one. And HQ plus 1, what I have, so the Q plus 1 also must be less than n minus 1. So at the end of the day, what it means that for Q less than n minus 2, HQX, so he will get 0, he will get 0. And if you have 0 here, the property of exact sequence will tell me that this map is an isomorphism. HQY. And maybe let's say let's go to this. Let's say this h n minus 1 also, h n minus 1 x. Here I have a 0 because q equal to n minus 1, also this guy is 0, h n minus 1 x. And then it goes to hn, and which a priori it is not trivial. And so this this actually will see that it contains a lot of non-zero element. But the theorem also says that at the end, this guy is a subset of this map is an inclusion, and so this is a subset of this one. In particular, the rank. Oh, sorry, I wrote. There is some. Where is the eraser? Oops. Let me see, where hn minus 1x and then h minus 1y. Okay. Anyway, whenever you see that I am talking something wrong, and you notice that it's wrong, even so you you think it might be wrong, it might be correct, then you can start interrupting me, no problem. Okay, yeah, at the end you see that this intersection, this restriction map, this map must be inclusion, and in particular the rank of this one must be less than the rank of this one. So this is actually the consequence. So let's go actually to the proof. So let's prove. Okay, so we learned the one statement from algebraic topology. So let's go to the proof. And during the proof, I will also need let's okay, actually maybe before going to proof, another statement. This is a kind of not so Thom-Leray-Gysin isomorphism. In some books it is called Thom, and in some article there are Leray, but at the end there is a Gysin, which we use this isomorphism to get a sequence, and it is called Gysin sequence. And also at the end, I think these three people contributed to this isomorphism. Maybe I tell also this one before going to the proof. Okay, so let's. So again, these statements are purely topological or C-infinity manifold. So that's why we just want to make the announcement. So y compact oriented and also x oriented. So in this context, it is the C. I am talking about C-infinity manifold. And of course, in our context, the orientation, maybe I have to mention this, all algebraic, smooth algebraic varieties and all smooth algebraic varieties, our complex numbers, they are complex. They are the subset of complex manifold, and all these are oriented. So maybe again one basic fact that in the complex geometry we don't need to take care about orientation because everything is oriented in a canonical way, and basically all this orientation comes from the orientation of C. That always for C we have this 1 and taking then the complex number I. But what I'm saying that then I want to introduce Thom-Leray-Gysin isomorphism, and in our case the orientation is no problem. And also in our context that we are going to apply X and Y are compact, but we will need just the compactness of Y. Okay, so let me just write down a very short version of the theorem. In the book I have written in homology, and there are more details. At some point during the course we will back to this theorem. But for the moment, let's just learn the announcement. So if you have two infinity manifold, let's say y and x, both oriented, y compact, then let me okay. So another thing, codimension of y in x is c. So this will be the real codimension. Well, actually, I mean, even let's not write it at all. The point that y and x are C-infinity manifold, though in the codimension in the context of C-infinity manifold. So let's write it. So this is an isomorphism of this type. Okay, the H m minus c of y. Again, the coefficients are all over z, even this theorem. This is isomorphic to hm x minus v. If I cut y from x and consider relative cohomology, m's relative cohomology, so here m equal to 0, blah, 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 blah. And then this will be isomorphic to hm minus c, m coming from here, c is the codimension. And well, by convention, h to the negative dimension of cohomology is automatically 0. So basically, this theorem, let's say, start the actually, there is some non-trivial statement also for 0, because it says that this part will be 0. So let's go put it as it is: 0, 1, 2. So the statement is about this relative cohomology x minus y. It will be hm minus c of y. And as I said, I will be back to this theorem in homology again. And the idea is that this map is very explicit, and actually it has to do with the intersection of varieties. But for now, the basic idea is that to prove Lefschetz hyperplane section theorem with minimum amount of ingredients. So so far we have learned the two theorems of algebraic topology. One of them is a short exact sequence attached to a pair y and x. Another is this Thom-Leray-Gysin isomorphism attached again to a pair, but the pair must be oriented. Well, at least y must be oriented, and the y and x must be oriented, and the y must be compact. We will not need the compactness of x. Okay, any question before going to the proof? Okay, so just a moment. Okay, so let's so this is this. Okay, two theorems from algebraic topology. Okay, let's go back now. Okay, in the middle of the proof, we will use also more statement from algebraic topology. Let's fix our notation. Zx. So remember that I had a z. That the whole, let's say the whole plane. Let's just consider at x. Then I have y. I have z. I will call the intersection x prime. And maybe another notation. By the way, if you want to, well, I will try to write down the things in cohomology. But basically, I am following the proof that it is stated in my book. If you want to open this part of the book, and it was section 5.4. here in front of the camera, I will try to reproduce in cohomology. Okay. So let's fix notation. Let me see what notation I need more. I need also to introduce u, which is x minus c, and v, which is y minus x prime. So let's try to write it. So when I cut z, I will call it u, and when I cut x prime from y, this will be v. And our main theorem, just with this notation, is just h q u v is equal to 0, q less than n minus 1. This is our main theorem that we are going to use. Okay, so let's start. So first of all, now the third statement from algebraic topology, the long exact sequence attached to a triple. So this statement is about arbitrary triple of algebraic arbitrary triple of topological space, but in our case it will be v inside u and u inside x. So whenever I have a consecutive inclusion of topological spaces, in algebraic topology we get also a long exact sequence. Okay, so let me write it. So the idea is that we want to learn a little bit also algebraic topology. Now I am trying to look my book and write down everything in cohomology. I hope that I will not make any mistake in front of camera. Okay, now so let's write it. Okay, I mean, this is good that I have h. Since h, let's say qxu, so hqxu, and then hq, maybe first I write it and then xv. Actually, I always prefer homology because it is better to memorize the order of the things. But since we started with check homology, let's just write as it is. And then hq plus 1 xu. And then maybe I write it here, so it is increasing, then it will be hq minus 1 u and v, and so on. Okay. Okay. Well, let's maybe in order to really memorize all these short exact sequences, maybe okay, let's just do in this way. So let me write in. So this will give this guy vu. The pair vu will be subset of vx, and then this pair vx will be subset of ux. And whenever you write in homology, you write, for example, first hquv and then hquuv and then hqxv and then hqxu. So this order is already repeated here. just remember that when you write cohomology and homology with boundaries, then you change the order. So this order comes from these inclusions, and at the end of the day, we have these long exact sequences. So in order to memorize the structure of this long exact sequence, maybe it is you start writing first write this inclusion of pairs. So this means that V inside V, U inside X, V inside U, X inside X, and then and so on. Okay, so the third theorem from algebraic topology. Whenever you see a triple of algebraic topologies, immediately you can write down cohomologies, actually with the coefficients in arbitrary ring or abelian group, but we will need just our integers. Okay, so let's go ahead. Okay, now we use our main theorem. We combine our main theorem with this long exact sequence. So if I want that this equal to be 0, and I want that this equal to be 0, what I will have this isomorphism. But in order to have this equal to 0 and this equal to 0, then here I have to assume that Q is less than n minus 1. Here I have to assume that Q minus 1 is less than n. Let me see. Yeah, n minus 1. And at the end of the day, so this means that if Q, let me, just a moment. Okay, sorry. I don't know what I'm saying. This everything here wrong with the theorem. Actually, that's true, but it is written. So Q not equal to n. Well, remember that in our main theorem we had the control of all the cohomologies, except all the cohomologies were 0 except the nth cohomology, and the n was the dimension of U. So this is, I was wondering that something fishy is going on. So this means that let's say Q not equal to n, and here Q minus 1 not equal to n. At the end of the day, if Q not equal to n and n plus 1, I have what? I have isomorphism. So here it is 0, here it is 0, then HQ XU will be isomorphism to HQX V. Okay, so the third theorem and our main theorem that we will prove it. At the end, they imply this one for this. Okay, so let's go what we need else. Okay, so now we apply Thom-Leray-Gysin isomorphism for pair U. Okay, let's for pair, let's say the UZ Z and Z inside X. Well, remember that U is at the end is X minus C. And as I said, in our context, everything is oriented. Z is compact. We don't need to worry about this one. So let's just apply this theorem. So HQ. So remember, so let's apply HQ. So X, the complement of Z inside X. By definition, it is U. So this is isomorphic to, okay, so the codimension of Z inside X. Now we have to return back to the concept of codimension. During the course that when I'm talking about codimension, it means the complex codimension, maybe codimension of, let's say, of Z inside X. It will this will be the complex codimension. Maybe then this will be twice this one will be codimension. So maybe I introduce some notation. Whenever I am looking Z and X as C-infinity manifold, that because the category of algebraic varieties, complex manifold, is much more smaller than the category of C-infinity manifold, maybe I write it just as I put infinity here. This means that I look them as C-infinity. So the complex codimension, twice it will be the usual C-infinity codimension. And it's, but the reason is that at the end, for us, the dimension of C is 1, whereas the dimension of the C's are 2, and then the real dimension of C is 2. And then let's say dimension of C to the n is for us is n, and but C to the n is R to the n, actually, taking imaginary and real part of the coordinates. And yeah, okay. So let's keep this in mind. Again, at some point next year, I will offer a course in complex geometry. All these things are usually covered in more detail in a complex geometry course. But let's return back. So we were applying Thom-Leray-Gysin isomorphism. So HQ, so remember that this was HQ minus the codimension. But Z is a hyperplane section theorem. Its codimension in X, complex codimension is 1. So its real codimension is 2. So at the end, we arrive at this this isomorphism. Okay, so so this is valid for any Q. It doesn't matter what the Q it is. So now we want to combine. Now we want to combine which this one. Let's say this one with this one. And once we combine it, what we get? So HQXU is this one. So let's say 1 and 2 imply that for that HQXV is isomorphic to so to this one, and this one is equal to HQ minus 2Z. So here there is no restriction for Q, but here there is a restriction for Q, which is Q not equal to N and N plus 1. And yeah, so we get this isomorphism. Maybe let's try to see in the picture. Remember that, okay, X was the whole space. The whole space, the affine part, V was the affine part of the the Y, and then the Z was this guys. And you see that it's a kind of a strange isomorphism because well, yeah. Okay, anyway, so let's go further. So we will use this this isomorphism. Let's go further. Okay. So again, long exact sequence. of the triple. Now we write the long exact sequence of another triple. V was affine open set, Zariski open set in Y, and Y is inside X. We will write this one. And then also I will write, what else I will write? And the long exact sequence of the pair. Both theorems we have already stated, X prime inside Z. Okay, so let's try to write, as I said, in the book it is written in homology, but let's write in H, maybe I just HQ, Y, V. I'm writing in this direction because I'm just making a copy of the version in homology and trying to reproduce in cohomology. And you will see that translating from homology to cohomology is not so hard. And then HQ, XV, HQ, YV, and then going on. Okay, sorry, there is a Q minus 1 here. And then here, of course, what it will be Q plus 1, 1, 2, 3. Then it will be Q, X and Y again. So then you remember that this is the cohomology that we are interested to prove something. So, and here it appears for the first time. So this is the long exact sequence attached to this triple. Now to this okay, to the long exact sequence attached to this this pair. Then HQ minus, actually I start from -3, and then you will see it later. Maybe it is not HQ minus 2. Let's HQ minus 2 Z X prime. Let's start reading this from here. So HQ minus Z X prime, and then HQ minus 2. Again, for me, writing these things in homology is much more natural. Maybe I write it and then we go. So in homology, you say that, okay, it is X prime. From here, we have the inclusion from X prime to Z, and then we have the inclusion from Z to pair of Z and the X prime, because this we consider the cohomology without boundary. And then we will have the boundary map from a Q minus, Q, this is Q minus 2, everything is Q minus 2, Q minus 2, Q minus 2, Q minus 2, and then the boundary map will go to Q minus 3. Okay, so yeah. Okay, so we already mentioned the short exact one to triple and pair. Okay, so let's I wrote this one in the bottom of the other one because there are some natural maps also in between the elements of this and this one here. So let's do this one. X and the V. Okay, so remember, okay, this was okay. This by our theorem was isomorphism, and this was by isomorphism. Remember that in our theorem, X V Q. Remember our the last isomorphism that we got. HQ XV is equal to isomorphic to HQ minus 1 to Z, where Q not N and N plus 1. And okay, so this this is from here. This is the one, let's say this one, y and v. This is by we have another isomorphism also here. And this is the y and v. Remember that y was the complement of x prime in y. So this is actually this is the Thom-Leray-Gysin isomorphism. In the same way, Thom-Leray-Gysin isomorphism here. We don't know. Well, in cohomology, I have to prepare, but there are really maps from here to here. In a moment, I will explain a little bit. But okay, let's look at this one. So this Thom-Leray-Gysin isomorphism for arbitrary q, but the isomorphism that we get here is for q not equal to n, and it's n plus 1. Okay. Okay, so anyway, there is let me see if we would do this one. This just a moment. This is Thom-Leray-Gysin. This is the one that we got, and then here actually I needed this guy here also. This means that there is some hq minus 1. xv going on here. There is q minus 3z going on here, and there are these maps. Then for this one, I have to assume that q minus 1 not equal to n plus 1. Okay. Okay, it's not clear. We got this isomorphism, but the point is that there are maps from here also. And in my book, I have written these maps in homology. And the idea is that these maps are given by intersections of cycle by varieties. But in cohomology, one can interpret them in terms of cup product and so on. But really, it will take us far from Hodge theory. But for the moment, a kind of a magic part of obscure part of this lecture, that these maps exist, and of course, if we constructed these isomorphisms, and the more importantly, that these diagrams commute. So this is a kind of part of the proof that at some point in the future I will return back when we discuss more the structure of Thom-Leray-Gysin isomorphism in terms of the intersections of cycles and so on. And okay, now what we have. So when we have this one, we have isomorphism, and then lemma. So this is actually the fourth statement from algebraic topology, that lemma 5, what it means that if you have a situation like this, long exact sequences of abelian groups, long exact sequences of abelian groups, the map from one side to another one, let's say from our case, in our case, from bottom to top. If this is isomorphism, this is isomorphism, this is isomorphism, this is isomorphism, then the middle one must be isomorphism. So at the end, it means that HQ minus 2 ZX prime will be isomorphic to HQ X Y. And under this condition. Okay, so basically we are near to finish. So HQ, we wanted to understand HQXY, and then it reduces to Z to the cohomologies of Z and X prime. And the situation is similar. Z is a X prime is a smooth hyperplane. Is a smooth hyperplane section of Z. But the point is that here X was dimension n, and and this Z is of dimension n-1. So this means that we are reduced to we have a similar situation with one dimension less. So this means that at the end we can repeat. Either we can use induction, or let's try to use induction. So okay, so that now the proof is by induction on n, the dimension of X. So let's try to do it. N equal to, I think, n equal to 1. I think it's okay. N equal to 1. N equal to 1 means that X is a curve in the sense of complex manifolds and algebraic geometry. So n equal to 1, I will have oriented surface of real dimension 2, and the y will be just a bunch of points. And what is what we want to prove? That h q x y equal to 0 for q equal to 0 and n-1, which is 0, because n equal to 1. So this is in n equal to 1 we don't need to prove something, because relative cohomologies with n q equal to 0, they are automatically 0. So n equal to 1, it's okay. So and this will be where n, that's n-1. Assume the theorem for n-1. So once we assume, then I have this one. So h q minus 2 z x prime is 0 for what? Q minus 1 to less than equal dimension of z. Dimension of z was n-1 minus 1. And yeah, so this is the given by the theorem. And okay, so this is the same as this is the n-2, and you see that at the end you will get for q less than n, you will get this equal to 0, and then you will get this equal to 0. But remember that we cannot replace in our main theorem this one, because of our induction. Because of our induction, at the end it will stop in n-1. So this is, and of course q less than n-1 implies this one. Okay, so this is a kind of let's say some basic idea of the proof. During this proof, we learned four statements from algebraic topology: long exact sequence attached to triple, long exact sequence attached to pair of topological spaces, 5 lemma, actually 5 lemma, not lemma 5, and which is a statement about abelian groups, and also this Thom-Leray-Gysin isomorphism. And there was also this piece, this obscure piece of our proof, that we had isomorphism here, here, and then I told that there are maps here also. In cohomology, they are constructed by coproduct, but I will at some point return back and tell how to construct this one in terms of intersection of cycles. But this is well, for now we are done. Okay, maybe any question before? Maybe I take a water. Okay, actually, we will learn more theorems from algebraic topology once we want to prove our main theorem. And maybe the rule for in this course will be this one. If there is some statement about complex or algebraic varieties, the idea is to prove them. But general statement about C infinity manifold, we have just to learn the statement and how to use it. Okay, so let's, I start sharing this, the page. Okay, so your window, a window. Okay. 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 So we have proved this Lefschetz hyperplane section theorem based on many other theorems in algebraic topology. Okay, so let me a little bit go to the previous section, a little bit talk about this obscure part of the proof. Okay. Maybe start just trying. Okay. Okay. So let me talk about a little bit section about this section. At chapter 4, homology theory. I didn't write too much about homology theory. And if I think it would be nice that in order to follow the course, you read this part. I have written a very compact version of algebraic topology here. So the idea is that at the end we have to get used to this one, and in this chapter it is constructed by singular homology. Even the cohomology is constructed using simplexes, and remember, and always they satisfy a certain amount of properties. Here I have listed a lot of all these properties they satisfy. It is written over here without, of course, any proof. And you can freely apply all these theorems to the cohomology that we defined by using covering and by check cohomology. And the reason is that in 1950s, around 1940s, when the people finished the construction of singular cohomology, they also started to construct the check cohomology, and they realized that the check cohomology and the singular cohomology, they satisfied all these properties also. And at some point, Eilenberg and Stinrath came to this wonderful idea that actually any cohomology theory one has to specify a little bit more. If they satisfy all these properties, they must be isomorphic. The moral of the story is that at the end, the check cohomology that we define will be the same as singular cohomology that we have. That's why we don't care really what kind of cohomology we are using, singular or check. And I think it would be just for reading, it would be nice that you read this part. And this one I put it as exercise in check cohomology, but here is actually, it can be a kind of exercise in singular cohomology. Okay, the construction of singular cohomology. I will do this part of the constructing of check cohomology. If you have seen, that's okay, but if you have not seen, we will be back. And the point is that check cohomology is much more adequate to intuition, whereas, well, singular cohomology is better for intuition, and check cohomology has less intuition. This is at least for me, this has been the case, because the cycles you can draw and so on. And so let's and during the proof of our main theorem, some of these properties of the cohomology we will use, all these theorem, universal coefficients theorem, and so on, excision theorem, Kuhn's theorem, and so on. But the idea is that I want to present the things in the middle of our main theorems. And the idea is to learn the same time we learn the topology algebraic varieties. Okay, so let's I took a little bit, actually it is already 1 hour. So I would recommend that you have a look for Thom-Leray-Gysin isomorphism in homology. Maybe in the 10th lecture I will be back, but you will see that it's an explicit isomorphism, and the map is really explicit, and it has to do with some intuition. And I just introduced the isomorphism. This is going to be isomorphism in cohomology, but in homology it is given by explicit map. So have a look to this isomorphism in homology. Let me see what I can else. Okay, and let me say. Okay, maybe I say something about Thom-Leray-Gysin sequence. Okay, so let's in order to finish the course, I tell the Gysin sequence, why the name of Gysin comes here, and then we finish the book. Okay. Okay, so let's Gysin sequence, which is the consequence of the short exact when attached to a pair, and Thom-Leray-Gysin isomorphism. So why it's the same as in Thom-Leray-Gysin isomorphism. So write down the short. Then write down the, where is the eraser? Write down the long exact sequence of not x and y, but this time x minus y inside x. When you write down this long exact sequence, then let's write down HQ. I'm very bad at writing in cohomology. HQYX, let's say HQX, oh, sorry, was supposed to do this one, x minus y, and then HQX, x minus y, and so going on. Once again, I am making let's mixture of the, so there is a restriction. Okay, so this is the restriction, and then yeah, exactly. Then so here it will be HQ plus 1 x y, and so on. So once you use, so if you use this let's say this Thom-Leray-Gysin isomorphism, this is HQ minus c codimension of y and x, then y HQX minus y, and then HQ minus c plus 1 y, and so on. And this is the Gysin sequence. This sequence will appear in our. We will use this sequence many times, and this is basically known as a Gysin sequence. Okay, so I think I will stop here. Any question? Maybe I stop. Okay, I stop recording.